Welcome to a new test and teardown video. This time it's a FLUKE 8800A Digital Multimeter. It's auto-ranging and it's 5 digits LED, and I believe this one was released in 1974. It's very, very heavy. When I first lifted this up, I thought it was maybe with batteries or something like that, but that is not the case. This is a bench only, mains voltage only, but it's just very, very heavy. One of my buddies found this in a trash can, so it's absolutely for free. I just checked eBay. There's one for $80 plus $30 shipment. So, I mean, if this works, it will be a very good day. But there is, it's a little bit sticky. I tried to clean it a little bit here, but I just didn't clean it. Ugh, here it's sticky. What is that? Oh yeah, we got some stickers or something was, yeah, there were, this is nasty. And the reason why I can't power it up is, see, this one is doing the flippity flappity, not working. So I need to open this, but that is super easy. So now we are inside, the outer cover is pulled out, and we still got some metal shield. Oops, okay. Okay, so that is how you do it. Warning. Oh, that is nice, look at that. All the different voltages and ohm ranges, some other bias calibrations. Everything is explained here. Master offset, differential offset. That is so nice. Oh, spare fuse. How cute is that? Look at that. So there's a spare fuse right here. Oh, I love it. That one looks a little bit weird. Got some bolts up there. Oh, what is that? That is probably, yeah, high precision resistor stuff. So the mains power entry switch is of course located inside this nice little shielded compartment together with the transformer, and it is very, very hard to push. It's like this spring is just very, very tough. And then there's an arm and a little funny joint in here. Look at that. And it's dingly dangly, and there's supposed to be a screw here that holds something, but the screw's there, but it's not working at all. I think maybe there's a little nut missing down there or something. So this explains why this stuff here is so flimsy-dimsy. But also, I'm not super happy about this switch being so hard to push. I mean, that requires this whole system to be really, really stiff and good. And there isn't any need for this switch to be so difficult to push. Yeah, other than that, the instrument is really, really nice and clean. I don't see anything that I need to do something about. All the capacitors here, they are nice and good. No signs of leakage. Of course, it's generating quite a lot of different voltages. So we got 3 rectifier bridges to handle everything here. And there's another custom chip. I guess that is doing more or less everything right. We got some LED driver chips. I expect that right there, right? It's probably multiplexed using this cable here. That's going to all the LEDs, LED segments, and that will be for the different ranges. I guess it's gonna activate this relay when I go through the different ranges. Did I mention that this instrument is actually a full 4-wire interface for your resistance measurements? And as you see right now, it's wired with shorting those little metal pieces here. That's the shorts between the source. Those two are the sources, and that will be the inputs. And you can leave those metal shorts here while you are in volt or AC or DC volt. It will disconnect the current source for resistance measurement, so that you can just keep them there. We've got 2 of them here on top of each other, and I want to move one of them down here so that ground is also relative to my chassis, and that way get a little bit less noise on it. But first I want to fix this switch that is doing dingly dingly here. So the bottom side here is nice and clean. Everything is tinned, and there isn't any solder mask like that. I don't know what is better, just to tin everything like this, or to add a solder mask so everything is isolated. If you get this a little bit dirty or moisture or something like that, you could probably create some leakage. So I think that a solder mask would probably be a little bit better solution. Yeah, you see some guard tracks and areas around things, also here, and tracks that just go without any endings like this one. That's also a guard track to avoid leakage. I did figure out this screw and the little bearing for the on-off switch, and look at that. Now that one works, and I look forward to power it up. Yeah. We got some, oh yes, I can see that. Got some big hefty parts in here. I don't know if we can easily take, this is ohm, it says ohm converter. That's funny, isn't it? So that's what that one is doing. Yeah, let's power it up and play a little bit with it and see if it is nice and good. Oh, look at that. Wire wound resistor with handwritten values. Isn't that cute? I was about ready to power it up, but then I find this. Look here in the middle of the picture. This can't be right. Was it really like this from the beginning, or is this somebody who took out this IC and plugged it in again? I mean, this is not correct. Oh yeah, by the way, here is the 7447. That is the 7-segment driver, as you can see here. And that one is of course connected to all the 7 segments. And then we got the transistors selecting the different parts of the digits, right? I took out the IC and you're not gonna believe this is how it looked. I mean, really? How can you be this ignorant when you plug in something and then obviously the instrument wasn't working, and then yeah, it goes in the bin. I think this is my lucky day. Look at that. Really nice and good switch, and it also seems to be working. Auto range is also working. I think I said 5 digit earlier in the video, and yeah, you could call this 5 digit. At least we got 5 whole digits and then an extra leading 1. So it's doing 200,000 counts, this instrument. So wow, I'm super happy about this. And I think it's actually quite accurate. I will dig a lot deeper into the accuracy later today, I think so, but I want to show you the auto range, how that works. So now we're very close to the next step. So then I give 1 more volt, and then see, it's going to go to the 20 or to the next range. So that must be the 200 volts range, right? And then we can just crank up the voltage in that range. So we got a very, very good resolution. And then let's see, we're now back to 20. And then I think there's like 3 or 4 volts hysteresis. So it's not going to go and flip backwards and forwards through the ranges like that. See? 18 and then, yes, 17. And then it flips to the previous range. How nice. There is a real funny thing here about the front layout. I don't know if you can see this. We got 2 indicators here. One says 200 millivolt DC or the 200 ohm range. Then there's an indicator here. Why is this important? Why do we need to know that? I mean, really? Why is that important? And then here, oh, if we are in mega ohm here, then there's also an indicator. Of course, this is when you go into auto and ohm. That means what? It goes here. I would expect it to go here, right? This is of course because in resistance mode, I forgot to put back these. I just double checked. Now they are mounted back again. We are in 20 mega ohms, and then this lamp is lit. And then we go to auto. What? Why are you doing this? Oh, this is funny. Why wouldn't it go all the way up? I mean, so I think the auto range is a little bit weird. So now I'm testing the different features, and one that's always a big challenge, that is the AC voltage or AC RMS. And in this instrument, I must say it is crazy how accurate it is. Let's even remove this other meter I was playing with. Look at the noises now. Almost gone. And what do you know? This is 1 volt RMS, 1 kilohertz. I am a little bit impressed, I must say. So I'm also testing the different DC voltages, ranges. I don't know if you can see this, but I am quite impressed. Look at the result here. This is 1 volt. Wow. And here is 10 volts. Look at all those digits. I am very impressed about the result here. And here is 100 volts. I think we should try and crank it up a little bit more, shouldn't we? And I believe this is 1000 volts. This is actually as accurate and as stable as I can possibly make it. Of course, I'm cheating a little bit. This here is a FLUKE, so FLUKE signal and voltage reference calibrator. So that is of course why I'm able to manufacture voltages like this. And look at that. Maybe I am taking it a little bit to the extreme, but of course I wanted to try the 4-wire resistance mode. And we got 200 ohms of full range. So that means it's actually able to write 199. So it's 199.999 ohms. That is the maximum we can see in this range. So at the moment, wouldn't you say this is about 10 milliohms, right? Let's see if we can get this in focus. I think if I hold my hand here, right? That is 10 milliohms. Let's see if I poke a little bit with the wires. Isn't that just amazing? So we got 1 milliohm resolution, of course, and if I change the position of the test hooks all the way in here. No, I was actually expecting to see a little bit lower value. So it's 10 all the way in there. Let's take it all the way out here. Nah, this is just noise from me touching the wires or something like that. Yes, maybe a little bit higher. I don't know. Let's look a little bit deeper into the unit. So we got those two plug-in modules right here. So the first one here is they call it the ohms board, I think. That's just funny. But this is doing all the currents and ranges and everything that has to do with resistance measurements. And in this shield box here, we got two very big read relays. So it's just for lowering the noise and all that kind of stuff. It's nice and tight in there. We got some more read relays over here and some high precision all in one resistor here. So yes, this is the current sources and all that stuff for resistance measurement. And the first board here, that is the dual slope AD converter. And yeah, it's just quite basic when it comes to dual slope conversion, really. Not a lot of fancy smancy things here. It's of course made with field effect transistors and all that stuff as well. The capacitor you see, oh, let me see if I can show you this here. This one down here, right where my finger was. Look at that big orange one. That is the dual slope capacitor. So it's a very large sized ceramic capacitor, and it is neatly located as far away as possible in the unit from power supply, anything hot, anything noisy. You see, it is actually as far away as possible to create as little noise pickup as possible. And it's also, all this is shielded, and you can imagine that any magnetic radiation and stuff like that is of course also stopped here by this shielding here to make radiation as little as possible. But in here, it's also shielded by the other board and by everything in here. So very well designed. And as you can imagine, this thing is running quite high resolution with the 5 digits and all that. So look at that, what we got right here. I believe this circuit is the reference circuit. It consists of U9, the reference chip. This is a 10 volt all-in-one reference chip. It's from Siemens and it's called a DH80417B. And this one is also used in the first series of FLUKE voltage references and all that kind of stuff. So it's a very, very good voltage reference. Actually, the data sheet says that this voltage reference is only 1 ppm per Celsius temperature change. And if you compare this to what is current new and nice, what you use in really good stuff today, LM399 for example, that will be half a ppm per Celsius. So this one is well, half as good, so to say. So the output from this voltage reference goes via those resistors here, super high precision parts, and then there's just a what I would call a regular op amp, LM301A, and it's not a super low offset or anything like that. Just a regular op amp, but in the quite good end when it comes to offset changes per Celsius or per temperature. So this is quite stable for the cost and complexity of this unit. So yeah, they did think about what they are using here, definitely. So I think I will end this video right here. Thank you very much for watching. Hope to see you soon again. Bye bye.